Friends, before we delve into the main content of this video, I want to take a moment to share with you a truly remarkable and widely popular video clip featuring the esteemed Professor Walter Lewin. This particular clip has garnered significant attention and is highly regarded.
That's okay, just take that off. Now comes an experiment which is emotionally the most difficult for me of this whole evening. I'm going to put my life on the line to show you that I'm really a believer of the conservation of energy. And you will see how I'm going to do that. I'm going to take the place of the glass. And I'm going to hold this object at my chin, and I cannot move any further back, so there's no cheat here. I'm going to release it right from my chin here. You realize, as you have just seen, that the slightest push, and this will be my last lecture, and no book signing afterwards. So I need your collaboration. When I count down from 3 to 0, no noise, no coughing, and I would even appreciate it if for those 3 seconds you would not even breathe. And I have to tell you something. I couldn't sleep all night. I'm going to close my eyes. I don't want to see it. And I'm going to count down from 3 to 0. 3, 2, 1, 0. I normally, after this demonstration, tell the class, physics works and I'm still alive.
So here, Professor Walter Lewin has demonstrated the conservation of energy very well. Now here, we will focus a bit on this ball and string system. So, in this video clip, this ball and string system is behaving like a simple pendulum. And in this video, there is a very perfect and brilliant description of physics. The pendulum has been used for centuries to measure time. And then, around the 1600s, Galileo Galilei became the first person to estimate the physical properties of this pendulum, and he presented some dramatic conclusions about the pendulum to us. In fact, Galileo proved that the time period of a pendulum, that is, the time it takes to complete one oscillation, does not depend on the mass that is suspended at the end of the pendulum. So, if we replace this ball with an object of heavier mass, even then, the time period of that pendulum will remain almost the same. You can see a description of this in another video clip by Professor Walter Lewin, where he himself is on the pendulum.
Okay. You ready? Okay. Oh, this really hurts. Can't you count a little faster?
6, 7, 8, 9, 10.
T with Walter Lewin. What is it? 45.9 plus or minus 0.2 period is 4.59 plus or minus 0.02. I told you, physics works.
So this video clip proves that Galileo's description was absolutely correct. Now, about 100 years after Galileo's work, it was extended further by Newton. He explained the entire dynamics of the pendulum. He showed that the motion of the pendulum completely depends on the length of the pendulum and the gravitational pull of the Earth. In fact, Newton proved this with the computation of the pendulum, that the Earth is not a perfect spherical object. So now our pendulum, which is in ideal condition, will always keep oscillating completely. It will never stop. But we all know very well that it is not possible to have ideal condition on the Earth. So this pendulum of ours will automatically stop after some time due to the resistance of the air, right? So whenever we have such a mechanical system which is oscillating but its magnitude is decreasing slowly with time. Well, you all must have heard this process of dampening in smaller classes. But to understand damping properly, we should have an understanding of imaginary numbers. Well, you will find many applications of dampening in real life. From your car suspension to every oscillation is carried by dampening. So whenever you study mathematics and physics related to dampening, you come across the square root of -1. Well, now we all know how to deal with this -1, but it took centuries for mathematicians to figure this out. So now we denote the square root of -1 with I. We also call them imaginary numbers. But to be very honest, they are not imaginary. Imaginary numbers are not actually imaginary. So now I'll tell you two definitions of iota, that is, the imaginary number. Look at your screen. First, it's written as I equals the square root of -1, and second, it's written as I equals 90 degrees. Well, by the end of this video, you will decide which of these two definitions is correct according to you. So first, let's understand where the square root of -1 comes from. Suppose I write an equation in front of you, y equals x squared minus 4. Try to find its solution. You put 0 for y, and then you can easily calculate the value of x. The value of x comes out to be plus or minus 2. Now let's plot this. After plotting, we get a parabola. Here, positive and -2 are its two solutions. But now, let me show you another equation here. Solve this one as well, y equals x squared plus 1. This time, when you try to find its solution, you find that the solution is 2 times the square root of -1. But what exactly is this? So we denote this as I. But why did we write it as I? Well, there's a history behind this, on which I've already made a separate video. So if you want, you can watch that, but still, let's take a brief overview of it here as well. Well, for now, let's try to understand this in a more intuitive way. So, suppose first we try to understand what numbers actually are. If you look at it intuitively, numbers give you a measurement of any physical quantity. For example, if I ask you how old you are, you give me a number. If I ask you how much money you have in your bank account, then you give me another number. Similarly, if I ask you how long it will take you to get here, you give me a number. Then again, you give me another number. So, we encounter these kinds of numbers in our day-to-day life, and mathematicians call them real numbers, and we plot real numbers on the real number line. In the same way, someone also thought that the absence of something can also be represented by a number, and that is 0. But if we go to the opposite side of this number line, then we get negative numbers. Now things start to get a little tricky here. When our number is positive, we know basically how much of something we have, what the quantity is. 0 means there is no quantity, but negative. If you think about it intuitively here, it's a bit tricky, because a negative number doesn't imply that the quantity itself is negative. Rather, it means that the quantity is the same, but we're looking at it in the opposite direction. Now in banking and money exchange, negative numbers are quite useful. So for example, if I give you money, you will have that X amount as positive, but for me, that X amount will become negative. That means it will become minus X, and if you look at it, there are quite a lot of applications for this. But here, an important property is that whenever you square any real number, the answer is always positive. Whether you take a negative real number or a positive real number, the answer will always be positive. So now, if we look at the square of the square root of -1, it comes out to -1. And this is not a property of real numbers, because if it were a real number, its square would be positive. This means that the square root of -1 cannot be a real number, and this became a stopping point for mathematicians for centuries. So mathematicians used to believe that if the square root of -1 appeared in your solution, it was assumed that there was no solution. But in 1545, an Italian mathematician named Cardano came up with an extraordinary idea. He created a new number. He simply invented it. However, he didn't call it an imaginary number or give it the name iota. In fact, it was about 100 years later that René Descartes, in a rather playful way, called it an imaginary number because he didn't like these numbers. He was not happy with the existence of these numbers. And then, about 100 years later, Euler finally represented it with the letter I. Anyway, moving on, we have another property in front of us, one that you've been learning since childhood. Whenever you multiply any number by a negative number, you get a negative result. So, if you multiply 2 by 1, you get 2 as the answer. If you look at this fundamentally and on the number line, you'll find that when you multiply by a negative number, you're basically performing a 180-degree rotation. On the number line, you're changing direction by 180 degrees, so multiplying by a negative number is equivalent to a 180-degree rotation on the number line, and we can actually sense this, right? But here, this happens on a single-dimensional number line. But what if we have 2 dimensions? Then if I ask you, instead of doing a 180-degree rotation, you have to do a 90-degree rotation, how would you do it? This is where imaginary numbers come into play. So, what should you simply do? For a 90-degree rotation, just multiply by iota, that is, by I. So suppose you take a number, let's say 4, and you multiply it by I, then in the vertical dimension, it becomes 4i. A 90-degree rotation has occurred. But if we want to rotate it another 90 degrees, you'll have to multiply by iota once more, so you'll get 4i times I, which is 4i squared, and we know the value of I squared, right? It's 1, so this becomes -4. So, what do you get when you rotate 4i by 90 degrees? -4. Now, if you look at it, this also makes a lot of sense to us because you started with 4, then you multiplied it by I to rotate it by 90 degrees, then multiplied it by another I to rotate it by another 90 degrees, so the total rotation is 180 degrees. And when you multiply 4 by -1, you also get a 180-degree rotation. So you can think of I as something that helps you visualize 2 dimensions in mathematics. Now see, whenever you add a real number to any imaginary number, you get a complex number, and this complex number can be placed anywhere between our real number line and imaginary number line. That's why we also call it the complex plane. Now these complex numbers have applications everywhere, like in differential equations, fluid mechanics, linear algebra, engineering, quantum mechanics, Fourier analysis, and many other areas. So in that sense, the imaginary numbers that seem imaginary to us are not really imaginary, but actually have a variety of uses. So you tell me, according to you, what is an imaginary number? Is it I equals the square root of -1 or I equals 90 degrees? Be sure to write the answer to the first question in the comment section. So, I truly hope that you have thoroughly enjoyed watching this video. If you found it enjoyable and valuable, please take a moment to show your support by liking this video and consider sharing it with your friends and family. Furthermore, if you haven't yet become a part of our community by subscribing to our channel, we highly encourage you to do so now so you won't miss out on any of our exciting future videos or important updates.